Mamunuzzaman, ESR 7. I'm doing my PhD at the University of Twente under the supervision of Professor Hans Watt. So my research topic is approximation for control of Port-Hamiltonian systems. So I show two direction of approximation of Port-Hamiltonian system. They are in some nature similar, like I am using database methods, so in frequency domain, but one is with I only know that this data coming from some passive systems, but I don't know whether it is rational or irrational. And another one is I need more information about the system. So yeah, so I will start with a general approximation problem. So if I have a linear time invariant system of n order, then the approximation problem is to reduce the order of the system by some r, and to get the realization of this full order system. And for that one, we have basically two different approach. One is projection based approach, another one is non-projection approach. So here I will show projection based approach. So the standard one is Petrov-Galerkin projection approximation. So here we have to choose two subspace of the original space, so that the approximation is in curly V subspace.
Okay, so maybe so on your screen you have a second slide, or because ours it didn't move. So can you go to the second slide?
Yeah.
Yeah, but we don't see it. We still see the first one. So Birgit followed.
Yeah, it's frozen because he went into full screen, and there is apparently a problem, I think.
Yeah, so I don't know. Maybe you should stop sharing and begin a share again.
Stop sharing. Okay.
You should share. He says, Mark says you need to share the screen, not the PDF. So go again on the green button. And can you go to the second slide? Yeah, now we are good. Please.
Okay, so yeah, so this is my two different approach that I already told. And so this is the general model approximation problem. So where I have a full order system and a reduced order system. And for projections, I have to choose two subspace. So one subspace for approximating the state, and another one where I constrain the residual, which is orthogonal to this subspace. Then I get this realization for this reduced order system. So now the question is how to find this matrix for this basis for the subspace. So one familiar way to get this basis is proper orthogonal decomposition. So as I am doing with frequency domain, so I present this technique in frequency domain. So the transfer function, if I consider a d equal to 0, then I can express with the input and output, and considering the input to 1. So I have the state space formulation and the transfer function with this state space. So I have data at a defined frequency point, and then I construct this snapshot matrix. So then this SVD of this snapshot, so which is used to to approximate this basis matrix. So we can use this QR, which is to approximate this original state space, and reduce the realization is like this one. So then I try to approximate this Port-Hamiltonian system. So I consider a special class of Port-Hamiltonian system because this skew symmetric matrix is not general one. It's a special structure. So Poisson matrix, and I also consider this space is even dimensional because later I will use symplectic projection where I need this even dimensionality. So like the previous one, the approximation is like that. So, but in our in general case, we cannot preserve this nice Port-Hamiltonian structures in POD or other projection methods. We have to select different methods to preserve this Port-Hamiltonian structure. So here we consider some symplectic model approximation. So first we define some definition. So the symplectic vector space is some space with even dimensional, and we define the symplectic form, which is just bilinear, antisymmetric, and non-degenerate. Then we call this vector space as a symplectic vector space. So the very standard example is the real space with the Euclidean inner product, where we use this Poisson matrix. So then with this inner product, then we can say this one is a symplectic vector space. So now we I define this symplectic mapping. So if we have two different symplectic vector space, then the Q matrix is called symplectic matrix when it fulfills this condition. So this one is it shows that it preserves this Poisson structure, but it reduces the dimension of this matrix or skew symmetric properties. So so all these metrics we define this stifle manifold which who satisfy this condition. Then for this symplectic mapping, we define an inverse left symplectic inverse in this way. So with this definition, we can prove all this lemma which we will use to symplectic model order reduction. So now the equation 18. So we can see it as a transfer function of the Port-Hamiltonian system can be seen as the solution of this equation, where I consider that dissipation is 0. Then if we choose a symplectic mapping from 2n to 2m, and if the data is in this range, so the empirical data is this range, and B is also in this range, then we can say that this reduced system preserve this Port-Hamiltonian structure. So, yeah. So we can now preserve the structure, but still we have to compute this basis matrix. So like as we know, there is POD where we use this snapshot matrix. So we get some data, and then we construct this POD basis matrix. So in a similar way, I construct this optimal problem where we have to choose this Q basis matrix, which is symplectic, and QL is symplectic inverse. This is similar in a nature that this is also an optimization like POD, but the computation is Q is much harder than this POD. So this, if we have this snapshot matrix, which we can split in a way, so we have already even dimensional, then we can extend this snapshot matrix like this S1. And if we consider this as Q1 matrix, where phi is a orthogonal matrix, then we can easily prove that Q1 is also a symplectic, and there is a symplectic inverse. Then we can say that this PSD, that what we call proper symplectic decomposition, is equivalent to this problem, which is a POD problem. So this is like when we use this original snapshot matrix, and this one is when we use the extended snapshot matrix. Then this harder problem makes to much easier, because we know how to compute this orthogonal in POD, how to generate this basis. So then I consider this Port-Hamiltonian with this dissipation. So this lemma I have used where K is a orthogonal symplectic manifold. That means it is symplectic and also orthonormal. Then T, the range of T and Q is equal, that we can prove. And it's just the straightforward calculation that if T is in symplectic, then it's the transpose of its symplectic inverse is also symplectic. So then in this theorem, so if we use this transpose of the inverse symplectic matrix as a projection, then I put here extra condition when the Hamiltonian is also in the range of Q, then this Port-Hamiltonian system also preserve, reduced Port-Hamiltonian system preserve this Port-Hamiltonian structure. So I applied this technique with a n-coupled mass spring damper system. So where I compared this PSD method with very much familiar IRCA, iterative rational Krylov algorithm method. So the PSD method is very close to this this IRCA method, and I also put the Nyquist plot, which shows that it also preserves this passivity of these mass spring damper systems. Then I go to another problem that with Loevner approximation. So where I have data, so frequency domain data, and I only know that this data coming from some positive passive systems, and I want to construct a transfer function which is positive real, because the passivity of the system is equivalent to the positive realness of the transfer function. So that is the problem that I already presented last 2 meetings, that if we construct a Loevner matrix, and then this is the algorithm to realize a system. But the problem is it doesn't formulate a positive real transfer function. So in theory, if the data, so if we construct a peak matrix with this data, and if this peak matrix is positive real, positive definite, then the transfer function would be positive real. So there is a similarity with this peak matrix with the Lovner matrix. So if we get the mirror image of this data, then this Lovner matrix is basically this peak matrix. So we push this condition to get this for this positive real transfer function. But for the system, this is not because that we raise this condition, but it's not fulfilled by the system. So that's why the approximation is not good. But there are some points for which this condition is also satisfied. That means if we have the original data, then the mirror image of the data also satisfied with this transfer function. And this point is called spectral zeros. So this is defined as the zeros of original system, and if we also adjoint system, then SG is exactly the spectral zeros. And we can see this G of S as the transfer function of this extended system. So from here, we can easily show that we can realize that there are mirror image of the complex plane, and if it's strictly passive system, then there is no spectral zeros on the imaginary axis. So that we can prove. Then this theorem says that if we can choose a set of spectral zeros of the original system and we use in the Lovner approximation, then this Lovner matrix is positive definite, which also gives us a positive real transfer function. But the problem is when we have only data, we don't know exactly the spectral zeros of the systems. So now this problem I convert to estimation of these spectral zeros. And this can be possible because this spectral zeros is a system indefinite. That means with the state transformation, the spectral zeros is not changed. So then we can apply one technique. So if we have, we applied this Lovner approximation twice. So from the first Lovner approximation, we get a realization, which is stable, but maybe not positive real. But then we can compute these spectral zeros for this system. And we know that this spectral zeros is also the spectral zeros of this positive real system if there is any state transformation exists. But we don't need to compute this transformation because we only need these spectral zeros. And we use this data for the second Lovner approximation. Then this matrix give a positive definite Lovner peak matrix, and we get a positive real realization. So this is used for this irrational transfer function because we are only using this data. So I have this boundary control system, and we have some irrational transfer function. So we need to approximate this one with a rational one. And I also want to preserve this passivity of this system. So this is the plotting. So I with the fast approximation, we show that there are some zeros. There are some poles in the right half plane, so it gives some unstable realization. But with this positive real, this this is a stable realization. And also, this is the approximation. So with the non-positive real almost fulfill this data, but positive realness at the lower frequency, they don't match that much, but most of the frequency range, they interpolate these data. And also, if I plot this Nyquist plot, I can see that this preserve this positive realness of the original system. So that is, I'm preparing for these two manuscripts. So one is for structure preserving for model Port-Hamiltonian system frequency domain, and the second one is data-driven rational approximation of irrational positive real function. And I'm also considering to extension of this work for parametric Port-Hamiltonian system, especially for in the second case. Yeah, that's all. Thank you.
Thank you.